Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone, we're very happy to have Andrei from Yandex in Moscow here to tell us about web graph models, properties and applications.
Okay, thank you very much for this presentation and for having invited me here. It's a great pleasure for me to speak in this audience. I'm sorry I have some problems with my throat. Probably I'll try to be as loud as possible, but I'm not sure. It's okay? Yeah? I don't hear it. So, okay. Yes, you hear me, okay. So I'd like to speak about web graph models, properties, and applications. I'd like to present here our recent results concerning classical web graph models and maybe some new conjectures and possible applications of these results. First of all, I'd like to present here some history of the problems. Of course, all of you, I think, know the history, but I'd like to present it anyway, since probably it's necessary to remind you some steps of this history. So, by World Wide Web graph, I mean, you know, the network which consists of sites, of hosts, and hyperlinks between them. So these are sites and hyperlinks between them. And of course, it's interesting to consider some, to invent, to discover, to consider some models which are very close to the experimental observations. So first of all, I'd like to present some experimental observations which were done in the end of 90s by Barabasi and Albert. I mean, I think you know, of course, that experimental observations by Barabasi and Albert in 1999 were, of course, as follows. First of all, the web graph is a sparse graph who has n vertices and mn edges. So m is a constant, and the number of vertices is multiplied by m. So this is the number of edges. The graph is, of course, sparse in this sense. Also, we have the well-known effect of the small world. The diameter of this graph is not precisely, but approximately equal to 5 to 7. And finally, the well-known property of almost any network, of a web graph, of course, as well, is the power law distribution of its degrees. So it means that the number of vertices who have degree d, where d is a constant or a function on n, over the number of all the vertices of this graph is something like some constant over d to the power lambda, where lambda is, by experimental observations, equal to something like 2.1. I have to look at the audience. You should know that, of course.
Actually, people work on many diverse things, so not everyone works on this.
Yes, yes. So that's why I remind you this history, of course. This is also useful. So these are observations, experimental observations due to Barabasi and Albert in 1999. The graph is sparse, the small world, the diameter is something like that, the power law of degree distribution. And now it's interesting to construct some web graph model which has almost the same properties. So this was suggested by Barabasi and Albert, and they also suggested some way to do that. So they proposed a very natural idea of the so-called preferential attachment. We consider at the nth step of the procedure, we add a new vertex n with m edges from it with probability of edge to a vertex I proportional to the degree of I. So if we have some graph which is already constructed, which has already appeared during the history, the story of its development, when we add a new vertex, which is called here n, we send m edges to some points, to some vertices from the previous graph, according to their degrees, proportional, with probability proportional to their degrees. So the probability of an edge from n to I should be equal to the degree of I in the previous graph over the sum of all degrees of j over all j in this graph. This is the idea. But unfortunately, Barabasi and Albert, who proposed to consider such a preferential attachment, they did not say any words about the distribution of these targets. So it's also necessary to say what is the distribution of these m targets here, since it's possible to distribute them uniformly or to consider some dependencies between them. So there is a problem with the dependencies between the m targets of this new vertex. And it's very funny that this problem, it leads to the following theorem, which is due to Bollobas. So the problem with formalization when m is greater to 1 is described here in this theorem by Bollobas, which says that given an arbitrary function f of n for n greater than or equal to 2, an arbitrary integer valued function with f of 2 equal to 0 and f of n less than or equal to f of n plus 1 less than or equal to f of n plus 1, here you see such that, of course, f of n goes to infinity as n tends to infinity, then there is a random graph process of this kind, which is depicted here with these probabilities, such that with probability tending to 1, t of n has exactly f of n triangles for all sufficiently large n. So it's possible to consider such dependencies here, that here we have an arbitrary given number of triangles in this graph process. So it's absolutely necessary to say what are the dependencies between such edges here, such targets. And the problem of doing that was solved by Bollobas and Riordan, who proposed the following well-known web graph model. Let us consider GMN, a graph with n vertices and mn edges with m, which is a natural number. So we're just trying to realize the idea that the number of vertices should be m times smaller than the number of edges of our web graph. Let us denote by dg of v the degree of a vertex v in the graph G. Now we describe the graph process for m equal to 1. So let G11 be a graph with one vertex v sub 1 and one loop, just one vertex and one loop in it. This is the first step of our graph process. Given a graph G sub 1 n minus 1, we can make G sub 1 n by adding a new vertex Vn and an edge from it to vertex Vi, picked from V sub 1, V sub n. You see here I can be equal to n, so we admit loops as well here. And the probability that I equals to S is given here due to preferential attachment just. So this is this ratio whenever S lies between 1 and n minus 1, and this probability equals 1 over 2n minus 1 for S equal to n. So there is a non-zero probability of a loop here. It's possible to obtain a loop, but it's more natural to obtain some link to a previous vertex of this process. In the case of m which is greater strictly than 1, we take G1mn, which is described here, which is found by this probabilistic process here, and we can make from it Gmn by gluing the first m vertices of this graph into one big vertex into, say, V sub 1 prime. Then we glue the next m vertices of this graph into the second vertex v sub 2 prime, and so on. So we obtain the graph whose number of vertices is exactly equal to n, and whose number of edges is already m multiplied by n. So we realize everything we wanted to realize. So this is the Bollobas and Riordan model, which is well known and which has already 10-year-old history, I think, and which is well studied, of course. It's possible to reformulate the same model, this model, in the following static way. It's possible to consider the so-called linearized chord diagrams. Linearized chord diagram with two mn vertices and mn edges is described here. We take two mn vertices, 1, 2, 3, and so on, 2 mn. We consider pairings of those vertices, and then we obtain a graph from such a construction in the following way. We go from the left to the right. We find the first right-hand endpoint of an edge here, of a chord here. And these four vertices on this picture, they are glued into a one vertex in our graph, and so on. This is the second vertex, this is the third one, this is the fourth one, the fifth one, and so on. So it's possible to consider this static model. We just take a uniformly random linearized chord diagram. We consider a graph which corresponds to this random linearized chord diagram, and this graph has the same distribution as the graph on the previous slide. This one, I mean. Is it possible to understand what I say right now? If you have some questions, please. So it's well known, of course. I'm just reminding you some previous results and some previous models. Now I'd like to proceed to some results which were obtained by different authors. So the first theorem, which is due to Bollobas, Riordan, Spencer, and Tushnadi, it says the following. If we take an arbitrary natural number m greater than or equal to 1, and if we fix an epsilon which is also greater than or equal to 0, then we can set alpha md equal to this value, 2m multiplied by m plus 1 over this product. And then with high probability, I mean with the probability which is tending to 1, when n tends to infinity, the number of vertices of our graph, then the ratio of the number of vertices of degree d, this is the number of vertices of degree d in GMN graph, over the whole number of vertices in this graph, is tightly concentrated around this value. So with high probability, this value lies between 1 minus epsilon multiplied by alpha md and 1 plus epsilon multiplied by the same value. But for every d only in the range which is depicted here, d is greater than or equal to 0 and less than or equal to n to the power 1/15. I think you understand that this is not very good, since for the real networks, for the real web, the number of vertices is something like 10 billions or something like that. But if you take this root of this value, this is smaller than 10. So it's not interesting to consider this. Okay. But in particular, with high probability, for all d in this range, we have this value equal to some constant multiplied by d to the power minus 3. Here d multiplied by d multiplied by d gives d to the power minus 3. And another theorem by Bollobas and Riordan says that for a fixed integer m greater than or equal to 2 and a positive real number epsilon, with high probability, this graph GMN is connected and has diameter which satisfies this relation. With high probability, the diameter of our random graph lies between log n over log n multiplied by 1 minus epsilon, and the same value multiplied by 1 plus epsilon. This is also very good, since in particular, if we take n equal to 20 multiplied by 20 millions just, we have log n over log n equal to something very close to 6. And if you remember, here it was 5 to 7. So this is very close to the expected value, which is just obtained by experimental observations by Barabasi and R. This is very good. However, as I've already said to you, there are some problems. The first problem is that we can take only this range, which is very small, from practical purposes, practical point of view. And the second problem is that here we have minus 3 versus c multiplied d minus 2.1 in the World Wide Web, as it was considered by Barabasi and Albert, and I've already told about it. So we have some problems in this theorem, and we have almost no problems in this one.
So you're saying the problem is that it's inconsistent with the web?
Yes, yes, it's a little bit inconsistent here. Yes, and also we have these technical bounds, which are not very good, of course, from practical point of view and from mathematical point of view as well. Okay. First of all, I'd like to speak about this problem. It's possible to remove it, to remove this gap. It's possible to remove this gap completely, and one of our researchers, Grechnikov, succeeded in doing that. So here, once again, the theorem by Bollobas, Riordan, Spencer, and Tushnadi. And here I put new theorems by Grechnikov. You see, the first theorem says that the expectation of the number of vertices having degree d equals just the same value as it's written here, minus something small, and plus big OM of d over n. So if you look at this theorem, you understand that first of all, there are no limitations like here, indeed. So it's not necessary to consider any limitations on d. If d is small o of n, if d is asymptotically small in comparison with n, then of course we have here an asymptotic formula up to the third term, 3-term asymptotic formula without any limitations on d. This is a very exact, a very precise formulation of the result concerning the expectation of the number of vertices having degree d in the Bollobas and Riordan model. Also, it's possible to prove here a concentration result of this kind. So if d depends on n and psi of n goes to infinity when n tends to infinity, then with high probability we have the difference between the number of vertices of degree d and its expectation. The absolute value, of course, of this difference is less than or equal to this value, which is small, of course. So for every d, not for d less than or equal to n to the power 1 over 15, we can prove a 3-term asymptotic formula, and we can prove a concentration result around this mean value. I think in this case we have removed all the gaps which could be removed here. So now it's interesting to speak about the second problem. What shall we do concerning d to the power minus 3 or d to the power 2.1? How can we
ask website to reduce the
yes. How can we try to produce such a model which is more close, which is closer to the reality? So to this purpose, many different models have been proposed. For example, there was a model by Buckley and Osthus. For the case m equal to 1, m, I remind you, is the ratio between the number of edges and the number of vertices. So for the case m equal to 1, and for a fixed positive integer a, we define a process exactly as g1n is defined above, but we replace the probability of an edge going to some previous vertex, say v sub s, by this value. Here we plus this number a, which is called initial attractiveness. So we consider some kind of initial attractiveness of any vertex. It's constant. It's the same for all the vertices. And it's denoted by a, which is greater than or equal to 0. And this probability is defined here. It's defined correctly, of course, since the sum of all such probabilities equals 1, certainly. And what can be said about these models? Of course, in the case of m greater than 1, we just consider the same process h, a, m, n. We identify the vertices in groups of m. And Buckley and Osthus, they succeeded in proving the following theorem. I don't know, maybe it's rather difficult to read it since it's very big. But be advised, a little bit later, I will show you much more difficult theorems, much more. So it's not a problem to consider this. It should be a problem to consider further progress here. So let m be a natural number which is greater than or equal to 0, and they be greater than or equal to 1. So both numbers are fixed integers, and let's consider this value. This value is rather cumbersome, but it's possible to consider it. Let epsilon greater than 0 be fixed. Then with high probability, the number of vertices of degree d in our new web graph model lies between 1 minus epsilon multiplied by this cumbersome value and 1 plus epsilon multiplied by the same value. So we have here a concentration result, but for all d in the range which is depicted here. So n is not to the power 1 over 15, but now n to the power 1 over 100 multiplied by a plus 1. 100, not 15. In principle, in particular, with high probability for all d in this range, we have this ratio equal to some constants multiplied by d to the power minus 2 minus a. It would be great, of course, if we could put here a equal to 0.1. Since if we take here a equal to 0.1, minus 2 minus 0.1 is exactly minus 2.1, and this is very close to what we have in the internet, in the real network.
Isn't it possible that by 99 this is not the right constant?
Huh?
2.1, couldn't it be like, something that was true 10 years ago, but now...
No. It's possible to check it right now, and the same constant is true. So we checked it, and the constant is still 2.1. Huh?
How did you perform the experimental?
It's some statistics over the web. We have.
If you work in search engine, you have a hypergraph, and you verify.
Yes, in Yandex there is a lot of information concerning real web graphs. So it's possible to make some statistics, some confidential intervals, and so on.
Of course, it's very tricky to get an unbiased sample because it's very...
Yes, it's very tricky. Yes, but it's possible to do so. So the constant is almost the same. But the problem is that, just a second, the problem is that a here is a fixed integer. So it's impossible to take a equal to 0.1. There is a problem here. So it's necessary to remove this problem concerning integers and the second problem concerning this very small range. And it's possible to do so. Grechnikov, the same Grechnikov as before, he succeeded in removing all the problems here. Here is the first theorem which is due to him. Let a be greater than 0, a fixed real. It's a real number. then the expectation of the number of vertices in this model which have degree d looks like that. This is an asymptotic formula which is not so good as the previous one, since here we have not 3-term asymptotic formula. This is only 2-term asymptotic. But here we have the asymptotic behavior of this coefficient, which is asymptotically something like that, which is equal to this. And now we can take any real number a, for example 1.0, and then we can remove this problem concerning the integers here. Also, it's possible to prove a concentration result. And in order to prove here a concentration result, we don't use Azuma's inequality. We don't use Martingale technique. We just use the second moment method. And we calculate covariances here. It's possible to calculate just covariances between the number of vertices of degree d1 and the number of vertices of degree d2. It's given here asymptotically, this covariance. And by using this result, it's possible to prove this concentration formula. So the number of vertices of degree d in our model minus this first term of our asymptotic formula is less than or equal to this value. It's possible to describe some consequences of this asymptotic result, this concentration result. So here I am trying to make it more clear. It's rather difficult to understand what happens in this right-hand side, but it's possible to look at some consequences. When d is asymptotically equal to some constant c multiplied by n to the power 1 over a plus 2, compare this to the n to the power a plus 1 over 100, no 100s, only n to the power 1 over a plus 2, no 100s, with some constant c. The expectation of the number of vertices of degree d is a constant, and this value is also a constant. But if d is already small o of n to the power 1 over a plus 2, also no 100s, then with high probabilities this value is asymptotically equal to the first term. Not expectation, but the same value with high probability. If d is omega of n to the power 1 over a plus 2, then with high probability this number is equal to small o of 1. Since this number is an integer by definition, then of course with high probability we have here 0. So everything is depicted here. No problem with anything like that. Only here we have not 3-term asymptotic formula, only 2-term asymptotic formula. I don't know whether it's so necessary to obtain so strict formulas. Maybe it's not necessary to try to take here to get here a formula with 3 terms. 2 terms is already enough. Okay. Now I'd like to proceed to another characteristic of the web, which is also very important, and it's not only interesting from mathematical point of view, but it's also interesting from some practical points of view. So I'd like to present before some motivations for considering it, and then I will define it exactly in mathematical terms. So let's consider the so-called link rings which appear in the internet, which are formed artificially by some people. So they look like bipartite graphs, which are close to complete bipartite graphs. Here we have a link farm, and here we have some link buyers who want to obtain many links from somewhere, from a link farm or from anywhere. Let's denote the sites which are on a link farm as a sub 1, a sub 2, and so on, a sub n. And let's denote link buyers by B sub 1, B sub 2, and so on, B sub M. So N sellers and M buyers. Suppose we have found such a thing. Suppose we have found such a construction in the internet. How to understand whether this is just a link ring or probably this is some natural construction which is not artificially done. Maybe it's possible to understand it somehow statistically. So let us consider the number of edges between farm and buyers. Let us denote by n the complete number of those edges. The first one, the second one, the third one, the fourth one, and so on. This is the number of edges between the left side, the left part of this bipartite graph and the right part of this bipartite graph. Let us denote by d of A2, for example, the number of edges coming to this vertex A sub 2. D of B2 is the same, the number of edges which are coming to the vertex denoted by B sub 2. And let's consider the value which is denoted by x of d1, d2, and the total number of edges linking a node with degree d1 and a node with degree d2. When d1 is equal to d2, we count every edge twice, but do not count loops which can appear in our model. Okay, so the expected value for n, if we consider some model of a graph, say Bollobas Riordan model or Buckley Osthus model, we can try to calculate the expected number of edges between this part and this part. And it's given by the following formula. N0 is equal to the summation over all possible vertices from the left-hand side and over all possible vertices from the right-hand side. Of this value, x of d of ai, d of bjn denotes the expected value of edges in our model between a sub I and b sub j. This is the expected number of edges between those vertices. Is it possible to understand it? Yes? So n0 is the expected value for n, which is written here. So if n is substantially smaller in some sense than n0, this structure can be a natural formation. And if it's greater than n0, this structure is probably a real link farm with some buyers. So one should only determine what should be a difference between n and n0 in order to say with high probabilities that the structure can be a natural formation and so on.
This I don't understand at all. I mean, so you have, you're looking over the web. There are many, many possible formations. So
yes,
some of them.
Yes, I use, for example, I use some algorithm in order to find some structures which are suspected to be link rings.
But
for example, I found 100 of thousands of such structures.
No, but
yes.
The problem, and what I don't understand is, n0 is the expectation once you fix the candidate nodes.
Yes, yes, I found a lot of formations. I take one of them, for example, and I'm trying to understand automatically whether this structure is really a link ring, not a natural formation.
Right, but first of all, but n0 is not an exceptional value, it's just the expectation.
Yes, right. It's an expectation which is given by our graph model.
Right, but let's suppose the graph model is completely accurate.
Yes.
Then, first of all, why can't a random variable exceed its expectation? And second, it could with some probability. Some probability it does. And second, you have many, many, possible formations. So in some of them, surely the number would exceed by far the expectations. I'm missing something here.
The algorithm that you're using is picking the places where this number is exceptionally high, presumably.
If we use an algorithm who tries to obtain all possible bipartite graphs, almost complete bipartite graphs, this algorithm would not work not only for linear time, but also for It will, yes, it will take exponential time.
But we're not looking at the algorithmic problem first. Suppose that you had infinite resources.
Yes.
Computational resources. We're trying to understand why, why you think of anything that exceeds n0 as something unnatural. It will, since the web is so big, you have many examples naturally where in your model that exceed the expectation.
But we have a tight concentration result. So if something exceeds expectation substantially, not like here, but substantially, not just n greater than n0, but many times greater than n0, of course we can suspect that.
Okay, so we didn't see the many times there is invisible print. So we didn't.
Yes. I tried to. Yes. I'm sorry. This is not so good written here. Yes.
Should depend on the size of the network.
Yes.
So this is somehow the whole.
Of course, it's some statistics. It's necessary to put here some constant c and here some constant c, which also depends on not even constant. Yes. Not even a constant, but something which depends on the number of these vertices, of course.
Right, but that seems to be the whole point. How, to determine this value.
So it's not just the number of vertices; it's the number of possible choices of a
you are absolutely right. It's a big statistical problem, and it's possible to solve it. But now I don't want to speak about this statistical problem. I'm just giving some motivation for the consideration of this value x of d1, d2, and n. So it's interesting to consider the distribution of the number of edges between links with given degrees.
Certainly interesting.
It's interesting since it's possible to consider this value, and another question, of course, is how to put here, what to put here, in order to statistically decide between two hypotheses. The first one is that this is a natural structure, and the second one is that the structure is probably a real link form. So I have 15 minutes, or okay. So I'd like to speak about this value. This value is much more complicated than the number of vertices of a given degree. It's much more difficult to study it from mathematical point of view. However, it's also possible to do it. And in fact, the results concerning the degree distributions are just some simple corollaries from the consideration, from the theorems which are due to the consideration of such values. So the first theorem here is given in a rough form, not in a very precise form, but it's written down here. There exists a function cx of d1, d2 such that the expectation of this value equals cx of d1, d2 multiplied by n plus something small. So this is also an asymptotic formula, and cx is given here by this rather cumbersome formula. This is not absolutely the most cumbersome formula from this talk. I'm sorry. This is a concentration result.
We are in some kind of competition.
Yes, it's possible to compete here, yeah. We are very close to the record, yes. So here the formula which is depicted here doesn't give an asymptotic behavior only if d2 over d1 tends to c, to a constant c which is not equal to 0. And the precise bounds, however, show that the term, this is the main term here, still gives the correct order of growth for cx, but the coefficient can be different, and in fact the coefficient differs. Oh, this is almost the record. This is the exact formulation of this theorem. This is some kind of the power and the glory. I don't know how to what to say about it. It's just here it's understandable, but here already probably not. But this is a correct formula here. The expectation of this value is given by this formula with such precise bounds. And another record concerns Bollobas and Riordan model, since here we considered Buckley and Osthus model, but here we consider Bollobas and Riordan model, and in this case we can prove even more precise asymptotic formula, which is still 3-term asymptotic formula. I don't know whether it's possible to understand something on this slide, but this is once again the power and the glory of this method. Now I'd like to proceed to some other definitions and to some other characteristics of the web graph. Here is the so-called second degrees. We define the second degree of a vertex T as the number of edges which go to the vertices which are adjacent to the vertex T. So this is the number of I and j such that I is not equal to T and j is not equal to T. The pair IT belongs to the set of edges of G1n. Ij lies in the same set of edges. We define by xn of k the number of vertices with second degree equal to k in this graph. I should mention here that we consider now only the case of m equal to 1. So here we have index 1, not an arbitrary m, but just the graph whose set of vertices equals to the set of edges, whose number of vertices equals to the number of edges. We succeeded in calculating the exact expectation, the asymptotic formula for the expectation of this value of the number of vertices of the second degree k in the graph G sub 1n. It also obeys a kind of power law degree distribution, power law distribution. Here this some remainders, and this is the first term of this asymptotic. And the theorem by Ostromov says that xn of k is tightly concentrated around this mean value, which is asymptotically found. So it's possible also to use such results in ranking somehow, since it's very important to know what is the second degree or the third degree or the fourth degree and so on of a vertex in our web graph. And some other calculations here. This is probably the most interesting things concerning the internet, concerning the web graph models considered in our work. And here it's also possible to consider the number of concrete graphs in a random web graph. For example, in Bollobas and Riordan model, here we consider the number of copies of H in GMN in the Bollobas and Riordan model. A theorem, even 3 theorems which were proved by Bollobas are written down here. The expected number of K3 of triangles in GMN is asymptotically equal to this value. So this is some constant depending on m, and this is logarithm to the power 3 of n. So the expected number of triangles in the Bollobas and Riordan model equals something multiplied by logarithm of n cubed. As for cycles, the expected number of cycles asymptotically equals to this value. And for the number of pairs of adjacent edges, it's also possible to find this asymptotic formula, which is depicted here. It's of course interesting to understand how to unify all these results. And in principle, in Bollobas work, it's possible to find some unification of this kind, but a much more readable and a much more understandable formula is given on the next slide, a theorem about arbitrary subgraph, which is due to Ryabchenko and Samosvat. For arbitrary graph H, fixed graph H, we have the following formula for the expectation of the number of copies of H in the Bollobas and Riordan graph GMN. This is some constant multiplied by n to the power. Here is the number of vertices of this graph H whose degree is equal to 0. Here is the number of vertices of this graph whose degree is equal to 1, and here is the number of vertices of this graph whose degree is equal to to 2. So, for example, if we consider K3 a triangle instead of H, then of course it has 3 vertices of degree 2, 3 vertices of degree 2 means logarithm to the power 3, 0 vertices of degree 1, and 0 vertices of degree 0. So here we have the same formula as on the previous slide. And it's very easy to calculate any asymptotic here for an arbitrary graph H, which is fixed. Probably I'd like to finish by that. Thank you very much for your attention.
So higher degrees don't appear here?
Don't appear here, yes. Only those degrees, yes.
Is it possible to sort of see intuitively why that?
This is not very good, in fact, since in the real internet this is not the case.
But can you see intuitively why it's the case for this model? Why degree 3 isn't right?
Maybe it's rather difficult to say it in few words. I don't know how to explain it. In this model, yes. Degree 3 doesn't work, but I'm sorry, I don't know how to say it in few words.
Questions?